I'm Rishi Ranjan, and today I'll be presenting our project, WinFuzz, which is a new targeted embedding-based fuzzer to fuzz Windows-based binaries. So first up, let's look at what the problem is that we're trying to solve. So as we all know that software bugs can cause real-world harm. For example, bugs like Eternal Blue, Heartbleed have caused an enormous amount of harm to all kinds of facets. Now, security analysts have the task of discovering these bugs and fixing them before they can cause any real harm. Now, there are multiple techniques for discovering bugs in a software. Some of the popular ones are writing unit tests, performing quality assurance testing, or doing manual analysis of the code or the binary to discover if it has any bugs. However, all of these suffer from the same common flaw. That is, all of these involve a human in order to perform these tasks. And as we all know, humans have limited speed and they can only get so much done in a day, or they have limited understanding and computational power. So, we look at an alternative way of testing programs, which is called fuzzing. Now, fuzzing is an automated software testing technique which can test millions of inputs in a day. It can find bugs that a human might miss, and it is much cheaper to employ than a human analyst. Fuzzing has been successful in finding bugs across all different kinds of software. It has found bugs in operating systems, browsers, hypervisors, and even bare metal hardware. And thus, we can say that fuzzing today is the first line of defense against malicious attackers, as these attackers themselves use fuzzing to find bugs in the software and then exploit them. And thus, a software developer must employ fuzzing to find bugs in its own software and fix it before the attackers done it. So there are three major steps involving fuzzing. First is the input generation, where we generate the input that is fed to our target program. The second is the execution, where the target program, which we'll call the fuzzing target from now on, or first target, is executed with the above generated input. And the third is the triage. We'll get to the triage stage in a later slide. But it has been observed that the most amount of time during a fuzzing campaign is spent in executing the target. Approximately 95% of the time is spent here. So, as Amdahl's law suggests, if we improve the execution speed or execution efficiency, then we'll have a more efficient fuzzing system in our hands. So this is a simple schematic of how fuzzing actually works. We generate test cases in step 1, then we execute our first target with those test cases, and then we triage them. What we mean by triage is we look at the behavior of the program with the test case and decide if this test case was interesting or not. For example, if we're looking for a bug which causes the program to time out, then an interesting behavior would be if the test case took more time than expected or more time than all the previous test cases, then it can be interesting or non-interesting, or it can even be a bug which will require further human analysis. These test cases are then saved, mutated, and then feeded back to the binary and so on and so forth. Now, on Linux, the execution mechanism in general is very fast. This is due to the fork system call, which is a copy on write style system call and makes process creation and process cloning very, very efficient. However, on Windows, there is no such equivalent, and thus, all the Windows software ecosystem, even though it is larger, fuzzing is much slower on Windows than it is on Linux due to the inherent kernel compatibility issues. So the challenge that we took on was that can we build a better efficient fuzzer for Windows binaries without using any additional kernel support, that is making it kernel agnostic. So first, we look at three different ways in which a fuzzer can execute a target. So the first technique is process creation, in which the fuzzer creates a new process for every test case or every input that it tests, and this process is repeated. The second is a fork server-based process cloning, in which fuzzer creates a target processes and it stops it after the initialization. And this stopped but initialized process is cloned every time for a new test case, which is executed with the test case, and the fork server is cloned again and again. Now this technique is much faster than the previous process creation technique, but it has its own flaws which we'll see. And the third and the fastest technique is called in-memory process looping. In this technique, the target itself has a loop, and the loop body is the code we want to fuzz. And the general execution goes like this: the fuzzer feeds an input to the process. The process then executes one iteration of loop, and then the fuzzer feeds another input, and the process goes through another iteration of the loop. This means that no new process has to be created, new process has to be cloned, and thus this is the fastest technique for process execution for fuzzing. Now, all three previously mentioned execution techniques have their own flaws, and which we'll look at now. So, process creation, which is quite clear that it is really, really slow, and it is up to 1,000 times slower than Linux is for, which is a huge overhead. Now, the custom fork server based process cloning, this has its flaw that it when you implement it on Windows, it requires a lot of Windows kernel API calls which are undocumented, and thus this makes the technique very, very Windows version dependent. That is, it is not portable across different Windows versions. Now, the third and last technique, in-memory looping, it is really fast. It is faster than all the above two. However, as we know that every execution of the loop changes the program state. So every new test case receives the process in a state that is not correct. That is, it has some stale state from the previous loop iteration. And thus, many binaries crash. And most of these crashes would be false because they are probably happening due to the stale state. Yeah. So we propose a new execution mechanism, which we call target embedded snapshotting. So the key insight that we draw from is that all the fuzzing relevant program state that an execution corrupts is controllable with language level constructs. And we'll get to what this means. And yeah. So what is target embedded snapshotting? So we build our implementation from in-memory looping, which is really fast, but it corrupts state after every execution. So the problem that we really face is how can we prevent this program state corruption? So the solution that we come up with is that we can inject code into the program, into the target program, in order to copy the program state into a snapshot. And then using this snapshot, we restore the state of the program after every execution or before every new execution. Now this would solve our correctness problem, and it would also give us the in-memory looping performance, which completely bypasses the process creation loop, and thus and this also requires no kernel support because all of this is done in the target itself using local state of the target. So we call our implementation WinFuzz. Now WinFuzz is based on coverage guided tracing technique, which is an existing technique for getting code coverage efficiently from a target. Now we base off our implementation on Winnie, which is one of the most popular Windows-based fuzzer, which implements coverage-guided tracing technique. In order to hook function calls in the target, we use Microsoft's detours library, which is an open-source function hooking library for Windows. Now, our implementation has 4 main steps that we follow. Number 1 is interposing on the target. Number 2, taking state snapshot. Number 3, tracking state changes. And number 4, restoring state. Now we'll look at each of this. So first up, interposing. What we mean by interposing is that when the fuzzer launches the target binary, then it also injects our dynamic library, the WinFuzz DLL, into the target address space. This allows WinFuzz DLL to look at all the state that a target binary has and copy it into the snapshot. Number 2, snapshotting. Now in this step, WinFuzz DLL simply creates a state snapshot of all the process state that a target binary has. Number 3, tracking. Now when the target runs, then during each loop execution, WinFuzz DLL also tracks all the program state that is actually changed during this run, and thus no extra state restoration is required, which gives us an extra performance benefit. And finally, after the target finishes its execution, then WinFuzz uses the existing state snapshot that it has, and it restores the modified state of the target binary. And thus we have a completely new target altogether, ready for another execution. Now we look at what all program states that we must restore in order to get a correct execution of the target. So there are four major program states that we must restore uh, for fuzzing purposes, and these reside on the stack, the registers, the heap, and the global variable. Now we'll look at each of them separately. So first up, the stack. What the stack holds is simply the process's local variables and the stack frame that each function call incurs on the target. Stack is a simple last in first out queue where variables are only added or removed from the top of the stack. Now stack pointer points to the top of the stack. Everything Now what we notice is that everything above the stack frame before snapshotting is from the last run, and thus resetting a stack simply means moving the stack pointer back to this location that is just at the snapshot point. Now we look at it pictorially, and as we see that this is the stack originally just before the loop execution. It has three stack frames and all the other stack frames are free. Now when the target runs, it adds its own local variables, new stack frames are added, and the stack pointer is moved below as well as the base pointer. Now after the target runs, we can simply move the base pointer to its original location that we have in our snapshot, and the stack pointers to the original location too, and thus our stack is technically restored as all the below frames are overwritten in the next run. Now the next state that we look at is the registers. Registers are one of the most important state that need to be resetted. These hold values that are currently being operated on. These also hold the instruction. A special register also holds the instruction pointer, and the stack pointer and the base pointer are also technically registers itself. Some of these registers may be parameters to the target function that we're trying to fuzz. And as we all know that parameters affect target behavior, thus it is of utmost importance to restore these registers to their original value. Now there are only two types of parameters. One are simple values, for example an integer, a character, or the other are pointers, where the register hold an address to another memory location. Now we simply reset each of registers to its own original value, as the pointer registers are also pointing to memory locations originally that actually exist. Now one key thing that we do is that we avoid returning from the target function so that we do not destroy any stack frames that could hold target parameters. This is the pictorial representation for the register resetting, where these are the original register values. RSP is A, RBP, B, C, and D, and these are copied into the state snapshot. The program runs, it changes all of these registers after the execution, where RSP is now A prime, RBP is B prime, and so on. And we use our state snapshot to copy the values, the original values, back to these registers, which restores the state. Now the third important program state that we look at is the heap. Now, unlike the stack, the heap is used to store variables that are dynamic in nature. Now, as we know, the stack is last in first out, but the heap, it is unordered, and the memory that you get from the heap has to be freed by the programmer manually. And thus, if you do not free the memory on the heap, it will keep residing on the heap across executions. This leads to memory leaks, and memory leaks are never good for a program. So an example could be that if a program leaks 2 kilobytes of memory after every execution, and if we run that in a loop for 10,000 times, it will just completely leak 20,000 kilobytes of memory, so which is a lot. So during resetting of the heap, we acknowledge that memory leaks are expected, and even small memory leaks can cause a fuzzer crash as they keep accumulating across execution runs. So in order to reset the heap, we simply track all the heap allocations and then free any that would leak at the end of each iteration. So for example, we have the initialization phase where the heap is empty and our chunk list is also empty. Now as the target allocates memory on the heap with malloc or realloc or calloc, all of these are added to the heap as well as to our chunk list. When the pointers are removed using free function, These are removed from the heap, and we also remove these pointers from our chunk list. And finally, after the target finishes its execution, whatever remains in the chunk list is freed by us, and the chunk list is emptied. Now we get to the final state, which is the global memory. Now, global variables influence the program variable quite a lot. So, and we know that global variables are stored in a special section of memory, which is separate from the heap or stack, which is called the BSS and the data section. There are two for global variables. Now, of course, target run would corrupt global variables for the next iteration. So in order to reset global memory, what we do is we copy the correct starting state for all mutable global section. That is, we look at the BSS section and the data section of the binary, and then we copy all the sections, all the pages from the section that are mutable. At runtime, modifying any page in the global section triggers our exception handler, which marks that page as modified. We install a guard page handler on such sections, and whenever any byte in that page is modified, it triggers the guard page handler, which notifies that this page in this section has been modified. And before the next iteration, we restore all the modified pages from our copy. So for example, this is the .data and .rdata section, and we copy page 1, page 2, page 3, page 4, that is all the pages, to the snapshot. Now the target runs, and we know that it has changed some global variable in page 1 and some global variable in page 4. This is notified to us by our guard page handler. And finally, after the target executes, we simply copy page 1 and page 4 from our snapshot into the target data section, and thus the state is restored. Now we get to the evaluation section for our fuzzer WinFuzz. So the criteria that we choose for evaluation are correctness, performance, compatibility, and bug discovery. Now we pit our fuzzer WinFuzz against two of the best fuzzers on Windows, which is Winnie, which is the current state-of-the-art fuzzer on Windows, and we use its custom fork server mode, and WinAFL, which is the most popular fuzzer on Windows, and we use its process creation as well as in-memory looping mode. Now the setup that we use are Microsoft Azure instances, which run Windows 10 Pro with Intel Xeon CPUs and 3.5 gigabytes of RAM, and all the fuzzing trial runs are run on the same setup. Now we run each of the fuzzing trial 5 times in order to collect statistically significant results as well as remove any non-deterministic thing that might occur. We also perform Man-Whitney new test in order to determine the significance. So the benchmarks that we choose for our fuzzer are these. Now we choose these benchmarks because of their proprietary nature as well as open source. We wanted a good mix of benchmarks, so we chose some from the proprietary software, since a lot of Windows softwares are proprietary. Then we also chose a lot of open source targets, and we chose targets which operated on a large variety of file formats. For example, we have file formats that are tar, png, wav, FLAC, etc. Now you can notice that WinFuzz was able to fuzz all the 10 targets correctly, while Winnie was only able to fuzz 7 correctly. It was able to run all 10, but it could not find any coverage, or it could not report any coverage for SMPDF, IrfanView, or JQ. Now WinAFL failed to run 4 of the targets from our benchmark list. Now let's get to the correctness test. Now in order to determine if our process creation and state resetting technique is correct, we use a very standard correctness measuring technique, which is the stability. Now in general, in fuzzing, higher the stability, more correct is the target. More correct is the target execution. So in order to compare our correctness, we use WinAFL's in-memory looping technique, since that is the only process creation technique that can be incorrect in nature. And as we can see, WinFuzz has a correctness of a stability of around 100% on an average, or somewhere between 98 to 100%, while WinAFL has really has bad stability in the ranges of 82 to 85%. Now, performance. What we mean by a fuzzer's performance in this case is that how many executions can it do in the same amount of time. So as you can see, our performance against Winnie's fork server mode as well as against WinAFL's correct execution mechanism, that is its process creation mode, is really significant. In uh, Against Winnie, we have a 7 times improvement over execution speed, while against WinAFL, we have a whopping 182 times performance improvement. Now, for code coverage. Code coverage is one of the most important evaluation metrics for a fuzzer. It tells us how much of the program logic was tested by the fuzzer. Now, our fuzzer WinFuzz outperformed both WinFL and Winnie on code coverage, and it found on an average 5% more coverage than WinFL and 15% more coverage than Winnie. Now, Man-Whitney mu test indicates that there was no significant difference between tar and there was significant difference for improvement over all the other benchmarks. While for WinAFL, we can see that uh, there was no difference for audiophile, while there were less coverage for 2 and more coverage for the other benchmarks, that is 3. These are the row values for our man-new test, and as you can see, and a row value of less than 0.05 represents a significant improvement. And as we can see, for Winnie, tar and audiophile are the ones that fail to have any significant improvement, while on WinFL we can see. Now, the one of the more important criteria that we had were kernel compatibility, where our claim was that our technique is kernel agnostic. It does not depend on Windows kernel's API features and thus can be ported across different versions of Windows. In order to test this, we ran WinFuzz. We tried to build and run WinFuzz and Winnie on different Windows versions. And WinFuzz built and ran perfectly on Windows 8, different builds of Windows 10, as well as with different builds of Windows 11. However, Winnie could only run on 2 specific builds of Windows 10. The developers of Winnie also state that they only claim for correct behavior of Winnie on a specific build of Windows 10. So Winnie is not kernel agnostic. Now, in order to see the bug discovery time, we compare the average time taken to find the specific bugs. Now, in this case, our benchmarks in our setup involved using older versions of some benchmarks in order to increase the bug count to have a significant data to look at. So we found 10 unique bugs across all the fuzzing runs and trials. Winnie was able to find only 3 of these 10. WinAFL was also able to find only 3, while WinFuzz found 8 of these 10. As you can see, there was one bug by Winnie which WinFuzz could not find, and there was one by WinAFL which WinFuzz could not find. Now, on an average, the speed up of WinFuzz's bug discovery time over Winnie is 1.56 times, while on WinAFL it is again a whopping 23 times improvement, where WinAFL sometimes took hours to find a bug, while WinFuzz found it in minutes. Now, although we focus on Windows fuzzing, the approach that we took is portable across different platforms as well as architectures. Now, targeted embedded snapshotting requires support for only hooking functions and injecting code, which are widely available features across different operating systems. So, for example, if we focus on OSs, uh, it would require just switching out the operating system level construct views with the new ones. And for example, if we were to implement targeted embedded snapshotting for Linux, we would simply use LD preload to inject our library into the target process and to hook functions. Set jump long jump instead of using get thread context and set thread context that we use to jump back, and push AD and pop AD and related instructions are all compatible, so we don't have to change any of our assembly. Now, portability to other architectures. In our implementation, only small part of it is architecture specific. We only have really small amount of assembly code in our implementation, and which is fairly standard. And even if we have to port it, we've done it for x86, but if we have to port it to ARM, all that we have to do is change a few registers, and that would make it ARM compatible. Thus, our technique is both operating system as well as architecture agnostic, and it can be ported to different systems. So, in conclusion, we built WinFuzz, which is the fastest and most effective fuzzer for Windows applications, and it gave us a better 32% better code coverage and a 72 times performance improvement on an average against the state of the art fuzzing in Windows.